Here we are, last talk of the afternoon, right? So we return from where we started with a speaker from this, one of the authors of this telescope conjecture paper. We have Jeremy Hahn, who is going to tell us about duality in K.
All right, so thank you, for coming on a Friday afternoon. I'm the last talk, so we should definitely thank the organizers for an amazing week. And I feel like, things are moving so quickly. Just this morning, I saw a conjecture with Alan and I made solved. We also have seen progress on chromatic splitting. I talked this week about covariant 1 progress at the primes 2 and 3, so everything's going really fast. And yeah, the other thing I wanted to do was thank the organizers of the whole semester, because that's also kind of coming to a close, and I think it's been a wonderful experience for everyone who's gotten to participate. All right, so everything I'm going to talk about later is joined with Sana and Jan Ragnes, who I've been privileged to talk to here this semester. And right, so I think before I get into that, though, maybe the title and abstract of the conference as a whole gave me license to philosophize about some conjectures or future directions. In particular, maybe there's some questions or future directions regarding the interactions between algebraic K theory, maybe topological cyclic homology, chromatic homotopy theory, and telescopic homotopy theory. And so maybe one question that came up in Ishan's talk that I really liked, and so let me emphasize it again, was this question of what happens in the descent spectral sequence for this map from the T2 local sphere to the T2 localization of the algebraic K theory of the K1 local sphere. And this algebraic K theory, right, so maybe there's some perception now that, that this is more computable than this, and the most basic question about what's happening with this map is what is the Hurewicz image, and using some knowledge of that Hurewicz image, we were able, collaborators, to bound the size of the homotopy groups of spheres to give new lower bounds there. But of course, the more refined question is just what is happening in this descent. I just wanted to maybe point out that there are some easier, or at least different analogs of this question that I think are also interesting. So you can ask also kind of Hahn local questions. What elements in LKN of S are detected by LKN minus 1, or LKN of the algebraic K theory of En minus 1 Hg for various G. Of course, you can ask that telescopically, but even chromatically, I think it's very interesting. And I put that up because I think it's actually kind of an approachable question. I think we now have the tools to answer questions like this. And maybe one version of that question that is its most basic, and I think probably very approachable, are the Greek letter elements in I star S detected in I star of the algebraic K-theory of mu. So I think algebraic K-theory of things that are either complex-oriented or maybe not too far from complex-oriented is now a very approachable subject computationally. And there are all sorts of questions of the flavor of when things are detected, or moreover, what happens in descent spectral sequences, I think would be interesting and approachable. Maybe let me give another remark on Ishan's set of questions. So, as was mentioned, Robert, Dustin, and Ishan constructed many finite Galois extensions of the Tn local sphere. And so for each of these profinite Galois extensions, including the cyclotomic extension that played a big role in the disproof of the telescope conjecture, you could enforce that Galois descent be satisfied. Or a priori, it might not be satisfied. It's exactly the telescope conjecture. Enforcing Galois descent gives Gauss field classes that are a priori between Tn local spectra and Kn local spectra. And so the obvious question that arises from their work is a question that I'm sure they're well aware of, is which of these are different. The telescope conjecture says that they're all the same. You could ask what is between SPTN and SPKN, and this is a sort of question about whether these specific things that are a priori between Tn and Kn local spectra are actually different, and when different Gauss field classes constructed in this way collapse into being the same Gauss field class. And I also want to add to this which redshift under algebraic K theory. So a very important component of the disproof of the telescope conjecture is that for the cyclotomic extension, that redshifts to the next cyclotomic extension one height up. And in particular, the Gauss field classes are connected. So you could ask whether Gauss field classes that are constructed in this way, or even more generally in any way, that you could construct a Gauss field class between these. When are those Gauss field classes connected by algebraic? All right. So in order to say anything about any of these questions, the sort of key new idea is that K theory is very computable. Right? That's why these questions have suddenly become perhaps approachable. And so how does one compute K theory? TC, ring spectrum. Right, and so I'm not going to distinguish much between K theory and TC because from the point of view of chromatic chromatopy theory and these computations at the prime T, if you will, of T complete objects, there's not a very substantial difference between K theory and TC. Hahn has shown us that that's really true in even more examples than you might have thought. So I'm very happy to focus on TC. So they're basically, well, one tool that of course I'm fond of is that for some ring spectra, but not all ring spectra, there is a motivic spectral sequence. For TC of R with associated graded so-called symptomic cohomology of R. Which is supposed to be maybe a version at the prime P of Voevodsky's motivic cohomology or the Tal motivic cohomology. And so one sort of problem with using this motivic spectral sequence, which I think is usually quite computable, is that maybe right now there's a condition on these rings, they have to be quasi-symptomic. In particular, the disproof of the telescope conjecture relied on understanding something about a not quasi-symptomic ring. But maybe I'll just remark that there's work on extending these motivic methods to more general things than quasi-symptomic rings, as indicated in Fenner's talk. The symptomic or motivic cohomology is naturally defined on synthetic E-infinity rings. These things that in motivic homotopy theory were called normed spectra by Hahn and Huihua and have the kind of power operations that give motivic Steenrod operations. So, I don't know, this is some developing theory, but you can just think about these functors from even E-infinity rings to spaces. And if you want to start asking sort of general formal questions about the behavior of symptomic cohomology, it's nice to have it defined on a category that has all colimits and all limits. This is some actual category of rings on which it's defined, rather than a restriction to very special types of E-infinity rings, like these smooth or quasi-symptomic ones. And so I'd like to highlight a theorem of Robert and Hahn, says that the functor takes rings to sleeves. So this is a functor from even E-infinity rings spaces, which is just maps in E-infinity rings from R to A. So this is a way of transforming any E-infinity ring into a synthetic E-infinity ring, one of these functors from even E-infinity rings to spaces. This is fully faithful on connected E-infinity rings. So you might think this is some very different category than just classical E-infinity rings. But if you're willing to restrict to, say, connective ones, you actually see fully faithfully inside of these synthetic ones, the usual ones. And so I think we can just view this as an enlargement of the category of pretty general E-infinity rings, connected ones. But this isn't going to be fully faithful on all E-infinity rings. So I want to remark that speed enforces the telescope conjecture. The telescope conjecture is automatically true for even E-infinity rings because they're all complex-oriented. And so speed will not be able to tell the difference between a Tn local ring and its Kn localization. Of course, Tn local rings are not really connected things. So I think the emerging picture is that you have some category of rings whose K-theory you can study using algebraic geometry by viewing them as synthetic E-infinity rings. And then from that, you have to do something that's fundamentally not motivic to analyze the K-theory of rings that have the possibility of failing the telescope conjecture. The motivic spectral sequence can be thought of as something like an Adams-Novikov spectral sequence, which you might expect not to converge when the telescope conjecture fails. But nonetheless, sort of the strategy of understanding this comes down to being able to understand very well things using this motivic spectral sequence, and then at the end of understanding everything we can about, say, connected rings, using that to study K-theory of more general rings. Maybe that from that point of view, the first thing to do is figure out what these new tools actually have to say about rings where they apply. So not rings that fail the telescope conjecture, but rather these kinds of synthetic E-infinity rings, connected E-infinity rings where the Adams-Novikov spectral sequence converges. All right, so maybe a goal that I hope to see developed, over the next few years is setting up symptomic cohomology and appropriate generality. So really writing things down in a generality where you can apply symptomic cohomology. There's not a category closed under limits and co-limits and things like that. So that's one goal. But then there are a bunch of sort of aspirational questions you could ask about that theory once it's stood up. So I'll highlight maybe two ones that I've been particularly interested in. So one that Andy has brought up a lot is this question of purity in symptomic cohomology. There are these wonderful theorems now that algebraic K-theory satisfies purity in the sense that the chromatic localization of algebraic K-theory only depends on certain chromatic localizations of the input. You can ask if that's compatible with the motivic filtration, so if symptomic cohomology itself satisfies a kind of purity. Another question that I think would be very interesting to understand better are steam rod operations. So that's a direction where you can ask, now that you have this symptomic cohomology theory, what are the operations between symptomic cohomology in different degrees? So the existence of the motivic spectral sequence gluing together symptomic cohomology and computing TC is giving a proof that there exists at least some Steenrod operations. There's Steenrod operations that build up the algebraic analogs of Steenrod operations building up for U from HZs. And so those we know exist, and it would be nice to better understand what exists in general and how these Steenrod operations might work. And in analogy with the motivic setting, you might even hope for other cohomology theories besides HZ and KU, like MGL, or things that could be built out of more sophisticated Steenrod operations. All right. Maybe that's enough of that. I want to discuss a little bit what this symptomic cohomology looks like in practice in some basic examples. So let L be a p-adic local field. The thing I have in mind is something like QP, or some finite extension of QP, and OL is a ring of integers. So you may think of ZP, and that's a plenty interesting example. All right, so then what can we say about motivic cohomology? Well, known by work of people like Ott, Schulze, Lurie, Morrow. If I do something like this, I'm going to get Galois cohomology, the field with coefficients in various Tate twists mod P. So these are both bigraded groups. Here you have a Tate twist and a cohomology group, and here you have a motivic associate graded and a pi star. And so you capture this Galois cohomology, and more generally, if you plug in discrete p-adic rings or discrete schemes, you will recover something about a tall cohomology of the generic fibers. All right, and one thing that just point out is that a classical fact about these Galois cohomology groups is that they are Poincare duality algebras. They have some kind of Poincare duality pairing. Called Tate duality or local Tate duality in Galois cohomology. Spectacular observation / conjecture by Asuni and Rognus that if I look at the I star Ger star note of TC of the atom summand mod PV1 and invert V2, this behaves much like many qualitative features in common with this example we were just speaking about. So in particular, conjecture is that this is a Poincare duality algebra. On many other similar features between these two bigraded rings. The reason I write this conjecture is that maybe at the time they were doing these calculations, there wasn't the language to talk about the motivic filtration, but they predicted that this motivic filtration exists and exactly how it should appear. maybe there's a more general proposal. Conjecture inherent in writings and talks of John Hahn, that there should be a class of rings vector B including maybe the examples of rings of integers, KU, the atom summing, KO, TMF, TN, which deserve to be called higher local rings of integers. The higher is now in the chromatic sense, where these have higher characteristic, except for this first example. All right, now there's a lot of things that that one could try to mean by this. In particular, I think an interesting question is what features of rings of integers in p-adic local fields generalize to these rings? And that's kind of an open question. Maybe it would be very valuable to have more analogies formulated as precise questions. But one thing that was highlighted very much by Johannes is that their symptomic homologies localized in the sense of inverting the I should be all gray duality algebras. It should satisfy Tate duality. So I will hopefully by the end of this sketch a proof that works for a general class of B, including these particular B's. Okay. I want to make a remark. It's a little bit about trying to see ways in which these behave like rings of integers that goes beyond saying that they have Poincare duality in their symptomic homology. So what is the general story here? Let me tell you a story about discrete things. So let X be a smooth, proper, formal CP scheme. Then the Untitled homology the generic fiber of X, the thing obtained from X by inverting T, that now lives over QP. This is a Galois representation. Well, the Untitled homology of anything over QP is going to be a Galois representation. But this wasn't a thing over QP, this was the generic fiber of a thing defined over ZP. And that equips this representation with a bit of additional structure, and sometimes called the crystalline structure. So there's some extra data on this representation that remembers that it came from something defined over the integers before we took the generic fiber. And there's a whole long story about these crystalline representations. So such representations are determined by what Jacob sometimes likes to call linear algebra data. So what you should think here maybe is Udine theory. Very similar, related statement. There's some somewhat complicated structure, like a p-divisible group, is actually controlled by something much more down to earth, which is some Udine module, feels more like concrete linear algebra. And so, yeah, wonderful thing about these crystalline Galois representations is supposed to be that they have some description that's less fancy than the full Galois representation. And so this data is data F gauge over Z. This is the most modern form of this. There's some linear algebra thing that's kind of like a Dieudonné module that's called an F gauge. And so actually, if you want to define the category of crystalline Galois representations, you just have to define this linear algebra data, this category of F gauges, which is much simpler to define. So this formalism of symptomic cohomology applying to ring spectra says that there is already a definition of F gauge over, say, the atom summand or Ku. We have notions of F gauges over all of these ring spectra instead of just over Zp. So some linear algebra data that directly generalizes the data that determines a crystalline Galois representation when you plug in a discrete ring spectrum. Okay, but the question is, can this notion of F gauge say over Ku, to give a simple example, be made explicit? So there's lots of theory by people like Drinfeld, Fontaine, Lafay, and others that have really, when I say linear algebra data, I mean something concrete that you can just write down. And there's some abstract machine using all maps into even E infinity rings, blah, 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 which we know is going to produce a purely algebraic category of F gauges, something that lives in classical algebra. But it's a little bit opaque what that machine actually produces. And by analogy here, we should expect that at least some F gauges should just be very easy to write down in algebra. And there should be a way of making this homotopically defined category of F gauges over Ku into some piece of linear algebra that could be explained to a high school student, maybe. But this is not yet terribly explicit. And you can kind of see the situation, right? So we would love to have some theory of Galois representations. It's like we would love to have some theory of p-divisible groups, but we have the theory of Dieudonné modules. So we're just very able to write down Dieudonné modules, but we don't have the other side of the Dieudonné equivalence. And so a question you could ask is there a group? And this has certainly been the main question, I think, maybe since the early 2000s when Yasuni and Ragnus was working. So is there a group like Galois, bar, associated to KU or any of these other rings such that F gauges, this category that has been defined, maps to representations for that group. Crystalline representations are special cases of representations. They're the ones that arise when you have something defined not just over QP, but over ZP. So what is the analog of representations of the absolute Galois group of QP that capture more than just this crystalline part, if such an analog exists? All right, so maybe that's enough philosophical questions. Let me tell you a little bit about how you might prove this duality and what conditions on V might qualify something to be a higher local ring of integers. Yeah.
Just to understand your first question, to make the definition more explicit, can you tell a little bit about what would the definition that is there already? Like you said that there is a definition of F gauges for all these things.
Yeah, so there's some stack constructed out of maps to even infinity rings, which I've talked about here, and I'm happy to tell you more, but maybe not right now. But even filtration defines an object of a pure algebra that's supposed to be the analog of this linear algebra data that defines crystalline representations. All right, so I want to talk about how you might prove Tate duality, which is one reflection of one sense in which these things behave like ring of integers. And this Tate duality is going to be something about localized TC with its motivic filtration. And the beautiful thing about TC as opposed to algebraic K-theory is that it's built out of THH. It's supposed to be much simpler. So in fact, this duality is going to be built out of duality that's already visible in THH. That's maybe the point, is that there's something about THH is a little bit more attractive. So versions of this duality have certainly been observed before, especially in a paper by Greenleaf. So this is sometimes goes under the name of Sunni-Boxted duality. Maybe it should be called Greenleaf duality, or maybe there's something already called that. But there's a duality visible in THH, which is just some kind of reflection of Tate duality in Galois cohomology. You can see this kind of explicitly. Let me give you an example, which might be useful to track without all these manipulations. So if I look at the homotopy groups of the topological Hahn homology of L, mod P, and V1, what does that look like? Well, that looks like a polynomial generator into an exterior algebra on two classes. The degree of mu2 is 2p squared. The degree of lambda 1 is 2p minus 1. 2p squared minus 1. So this is you might know that the THH of Fp is a polynomial ring on this Boxted class. This is a similar kind of Boxted class, but we also have this exterior algebra floating around. And I will just notice that mod mu2, this is a Poincare duality algebra. So it's not actually maybe got Poincare duality immediately, but if we mod out this Boxted class, we get an exterior algebra which manifestly looks like a little finite self-dual algebra. I'll also maybe even say that inverting U2 gives the Poincare duality algebra. Maybe don't worry about that if that seems weird to you, but it'll now be a duality algebra over the graded field FP adjoint U2 plus minus. So that's an example. What is one way of sort of maybe anticipating in advance that you should have seen some duality there? Something that's a more general argument than an explicit computation for the atom sum in. So let's suppose B is a connective B-complete ring where I0P is one of these rings of integers, maybe like ZP or something. And let's call the residue field of pi 0 K. Maybe this ring of integers is ZP and its residue field is FP, ring of integers mod P. Okay. Let us suppose that K is perfect as a B module. So there's a map from B to pi 0 of B, which is connected. Pi 0 of B maps to its residue field. It gives a map from B to this finite field K. And that makes K a B module. And we ask that it be in the thick subcategory generated by B itself. So it can be built in finitely many steps from B. And let's look at these examples. So if I take the ring of integers, I can mod out by a uniformizer and get the residue field. So I can build the residue field in just one cofiber from OL itself. For KU, I need two cofibers. I mod out by P and the bot element, and I'm left with FP. For L, I mod out by P and V1, I'm left with VP. Again, that's just a finite amount of coning off. For KO, I could first mod out by eta, and then by P and then V1. And there's similar things you can do for TMF. One feature that I think is probably extremely important for something to be called a higher ring of integers is that the residue field should be constructible in finitely many steps from the ring itself.
Does the number of steps seem to scale with the height?
Well, in some loose way, but of course KO, you need an additional step for eta that is not really about the height. But maybe there's something there. All right, so let's just start with only these two assumptions and see what we can say. First of all, I can look at K tensor over B with K. And take the homotopy groups of that. And what is that going to be? That's a finite connected graded Hopf algebra. So it's a Hopf algebra because it's the sort of thing that appears in a descent spectral sequence. Since K is a field, it's not Hopf algebroid, but a Hopf algebra. It's connected because we assumed B was connected. And it's finite, that's the key point here, because you can build K out of B in finitely many steps. All right, and such things are known to always be Poincare duality algebras. So maybe the example would be B equals KO, and then you get this little algebra A of 1, which is got a symmetrical picture. So in general, if E is a ring and M is a bimodule, we can talk about the THH of the coefficients in that bimodule. Again, THH is supposed to be something very explicit and not too scary. So this is B tensored over B tensor B op with N. Bimodule is just a regular sort of module over B tensor B op. All right, and then we can observe this example we're studying THH, the atom summand mod PV1. Another name for that is THH of the atom summand with coefficients in its residue field, the residue field FP. Yes, FP is obtained from L by modding out by P in V1. So maybe the general thing to be looking at now is in this generality of a B where K is perfect, we can consider the THH of B with coefficients in its residue field as a bimodule. And that's where we will first see the duality in THH. All right, now there's a little maneuver you can do, which is maybe not completely obvious. It's sometimes called the cyclic invariance of THH. You can rewrite this. This is just some completely general thing. This is the same thing as the THH of K with coefficients in bimodule of K tends to be of K. That's one of these kind of maybe surprising but elementary maneuvers that's common with THH. And now we look maybe like we're getting closer to a statement where we already have seen some duality. The Whitehead tower for this object in the category of K bimodules gives a spectral sequence. It starts with the homotopy groups of K tensor over B with K, tensor with THH of K, converging to tensor over K, converging to the homotopy groups of this guy. Which again is just another way of saying THH of B with K coefficients. So this is a spectral sequence that is pretty simple because again, this is just a finite K module because you can build K infinitely many steps from B. So this Whitehead tower is a finite filtration. And so therefore, this spectral sequence has a horizontal vanishing. Just because the filtration defining it is finite. What does this look like? K is a finite field, so it's a perfect field, and so the spectral sequence begins with the homotopy groups of this connected graded Hopf algebra tensored with just K adjoint of Boxted class in degree 2. That's what the THH of a finite field looks like. For Boxted. And this is obviously a Poincare duality algebra I invert or mod out by mu0, but in fact this is a Poincare duality algebra mod mu0 to the p to the j for any j. If I mod out any of these classes, I'll get a Poincare duality algebra. And so one thing to note is that some power of mu0 survives the spectral sequence. Why? Well, because the spectral sequence has a horizontal vanishing line. So maybe there's some differential on mu0, but then mu0 to the p will survive that differential by the Leibniz rule. And mu0 to the p will have to have a longer differential. But eventually there's just no room for differentials because of the horizontal vanishing line. And so some power of mu will survive. And in this example, it's mu0 to the p squared. It's not as though mu0 will always survive the spectral sequence, but some power of it will. Mod out by whatever power is a permanent cycle. And we'll be left with some spectral sequence that starts with a Poincare duality algebra, dualizing classes in the largest possible degree, and that means that it cannot be killed by any differentials. And so no matter what the pattern of differentials are, this must end up as a Poincare duality algebra, regardless of differentials. Poincare duality algebra. Very happy when John explained this argument to me. It seems very general, and we see already this duality in THH. So in the final minutes, I will try to say how we upgrade this duality on THH to a duality on TC that, in the classical case, is tape duality. Angular theorem is work in progress by Sarnoff. I'll say it's work in progress for E, satisfying some conditions. And maybe the point is that we haven't really completely settled what conditions we want to make this theorem maximally general. Maybe I think it will be fine if I just explain how this theorem works for the atom summand, and I'll indicate some arguments that will make it obvious that it should apply to a much more general class of rings than just the atom summand. So what does the theorem look like for the atom summand? For integers, A, there is the diagram. So I can take first star mode, DC of the atom summand, mod some power of P, some power of V1, and some power of V2. And I can map that to the Anderson dualizing object, except this is now a sort of synthetic Anderson dualizing object, if you like, because we're in first star mode. This is define Poincare duality pairs. So I said that I said that we were going to prove duality when you invert the VI. What I'm claiming here is that there's a Poincare duality when you mod out by the VI. So it's not quite something that generalizes state duality yet. But if I have this integral that makes this a Poincare dual algebra, I can restrict it to what happens when I don't mod out the last one. And I could instead try to invert. And then the claim is that there exists a unique thing filling this diagram. So the Poincare duality upon inverting V2 exists and is determined by a Poincare duality that exists when you mod out by V2. It's kind of a common trick in this subject, used also in the disproof of the telescope conjecture, that to analyze something after inverting a VI, you can try to analyze it, mod that VI, which is a little bit strange, but it works in the presence of this Quillen-Lichtenbaum property, which is very important in the subject. Word sketch. Since FP is a perfect L module, again, our all-important condition showing up, there's a transfer map from the THH of FP, say even the TC of FP, to the TC of L. So there's a wrong way map, a transfer map that comes from the fact that TC is something you can apply to categories, and there's a functor from perfect FP modules to perfect L modules given by restriction. So I can mod out by my favorite things. And it's a little bit funny because here I'm modding up by 0 a lot of the times, but nonetheless I can do it. And the claim is that the dualizing class, sort of top degree of Poincare duality, is in the image of this transfer map. So using the transfer map, you can produce a class that you want to be the top class. And we even saw a talk about how you can produce the top classes in Poincare duality algebras by transfer maps earlier this week. And so,
are there any kind of hidden twist by suspensions here or anything?
I think this map has no suspensions.
There is a suspension in the eye, on the right
I
hand.
is suspended. Okay, so you can define the class, and in fact, this same Quillen-Lichtenbaum property, this useful property, will tell you that this dualizing class is non-zero. It's in this image, and you can use this Quillen-Lichtenbaum property to show it's non-zero. And so now we have a class that's non-zero. It's actually alone in its motivic bi-degree, so it defines the dual class, an integral. And in the last 20 seconds, I'll say, if you have the Poincare duality class, how do you prove you get a Poincare duality algebra? Well, in general, if you have some manifold, you can study Poincare duality on it using a handle body decomposition. And for reasons of time, let me just say that you can glue together Poincare duality on a big manifold from Poincare duality on submanifolds, and you have to check some orientations. But if you already have a dualizing class, somehow checking the orientations is not really the point. And the point would just be to already know that you knew Poincare duality on the submanifolds. And then we would have to glue to some Poincare duality on the big manifold. And in this case, the submanifolds are things built out of THH, where we saw exactly that duality. So we build TC out of THH, and then we can reduce to this THH duality using the fact that we already have a candidate dualizing class. So thanks for bearing with me.
Questions for Jeremy?
Can you say that a little bit more slowly? How we could do THH is analogous to a submanifold TC?
So there's this beautiful picture in John's webpage, where in his talk section, where you can see something about this. Here's some picture of a manifold. Maybe you can think of a big manifold as something where you glue together these two ends of a closed manifold. So maybe this is TC minus of L mod P V1 V2. This is TP of L mod P V1 V2. And this is the Frobenius and canonical maps. So maybe you just have to prove some kind of duality on this and some duality for a manifold with boundary here. And so there's this really nice fact that this is the same thing as THL H of L take CP mod PV1. So a useful fact in this business is that modding out the last VI is related to modding to just passing to something involving THH more directly. And so there you actually just see this kind of duality in TP mod all the variables with this duality in THH that we already saw before. And maybe that's enough for now.
Can you say a bit more about what I is? In particular, what can you say what its homotopy groups are?
It's the Anderson dual of the motivic sphere, if you like.
Is it like FP mu mod mu to infinity or something like that?
It's the Graham-Cohen's tool of the sphere. So Hundevig groups are the rules of the groups of the spheres.
Okay.
So I should think like MU synthetic? Or should I think more sophisticated than that when you say the word motive?
You should just think MU synthetic.
Very good.
Since we're working with Gerstar, maybe even just sheaves over M of G.
In particular, is there some reason why you call it Anderson instead of Graham-Cohen?
No.
So I guess normally there's this bigraded shift on I.
Yeah, there's definitely supposed to be a shift there.
Will it depend on the ABC that you chose?
Well, it will, but in a way compatible under the A, B, and C. So I think you can describe the whole thing as a map from TC of L mod P to the infinity, B1 to the infinity, B2 to the infinity.
Any questions? I have a quick one. In the earlier part of this talk, when you were talking about conjectures, we were talking about the F gauges and the hypothetical group. Is this connected at all with some of the things that Samak was talking about in his talk? Or is it not at all?
I don't think it's that closely related.
Okay, no. Want to understand.
He and I were both reducing to algebra from topology in a similar way, but from different topological inputs.
Gotcha.
I was wondering.
So you said, we, like, earlier in that talk, you were saying we have these gamma representations that come from CP, and so they have something with CP, and so they have this crystalline structure. And I was curious if you know, so if I have a Galois representation, then I can get an automorphic representation from it. Does the crystalline structure need anything there?
I'm not the right person to ask this to.
All right. Thank Jeremy again.